In this video, we will talk about two notions that will be important when we talk about the Zariski topology, but they can be defined for any topological space. And those are the notions of connectedness and irreducibility. So take a topological space X, a space with a topology. Then if you can write X as the union of two proper subsets, each of which is closed and disjoint, each of which is closed and they are disjoint from each other, then X is said to be disconnected. And if it's not, then it is connected. And if you think about what it means, say, for intervals of the real line, this would be what you mean, because if the interval is connected, you cannot split it into two closed disjoint subsets. If it's disconnected, you can, because each connected component will be closed. Another notion that you might not have seen in connection to other topological spaces is that of irreducible and reducible. So if X is the union of two closed proper subsets, then it is reducible. Otherwise, it's irreducible. So what is the difference? The difference is when we talked about connected, we required the subsets to be disjoint. Now we just want to have two closed subsets that are proper and that are not necessarily disjoint. So you might think, but isn't this trivial? Doesn't this hold for most topological spaces? Say you take the real line with its usual topology and you take any interval, then you can surely do this thing, and then it is the union of two closed subspaces. And indeed, this is the case for that kind of topology, but for the Zariski topology, this is not the case. We will see the peculiarities of the Zariski topology very soon. And so from the definition, it follows that every irreducible topological space is connected, but not conversely. So let's take an example from Zariski topology. We have the set of all x and y in A2 such that the product is 0. So this is this so-called coordinate cross. And if this is x, then you can define x1 as the set of x, y, where y is 0, and x2 as the set of x, y, where x is 0. So this is x1 and this is x2. And since both are given by zeros of polynomials, they are both algebraic sets, so they are closed. And so we have managed to write our space X as the union of two closed subsets. They are not disjoint, they intersect in this unique point, the origin. So as I said, the Zariski topology is a weird topology and has some unusual properties already when looking at something as simple as the affine line. And this weirdness comes from the fact that it's different from our intuition. So this slide is especially important to you who has worked a lot with other topological spaces. So the topology is very coarse, meaning that there are very few open and very few closed subsets. It is not at all the situation where you have a whole amount of open intervals to deal with. So if you look at proper subsets of the affine line, so what is a closed subset? A closed subset is the zero of some set of polynomials in one variable. But as we have talked about, this can only happen if the set is closed. No polynomial, if the set is finite, no polynomial has infinitely many zeros in the affine line. So in other words, the only closed subsets, aside from the empty set and the line itself, will be the finite subsets. And this means that the open subsets will be the cofinite subsets. So they are huge. So if K is the complex number, this means that the only open subsets you are going to have are the whole complex plane with a finite number of points removed. So keep that in mind when you say that you take an open neighborhood around some point. This open neighborhood will in fact be the whole space minus a finite number of points. In particular, this means that A1 is irreducible. You cannot write it as a union of two closed subsets. Because remember, our field is algebraically closed, so it is infinite. So it will have infinitely many points. A1 has infinitely many points, and all closed subsets have finitely many points. A consequence of that is that A1 with this topology is not Hausdorff, meaning that if you have 2 points, then you cannot take an open neighborhood around one point and an open neighborhood around the other point in such a way that these open neighborhoods do not intersect. You cannot separate points. This situation, where you have a point X, a point Y, enclosed in their open neighborhood, gives you the wrong intuition. Because all the neighborhoods, all the open neighborhoods, will be the whole affine line, with the exception of a finite number of points. So they will intersect in such a huge set as well. And much that lies behind this is in the following remark, that if you have any irreducible topological space, then an open subset is either the empty set or it is dense in X, meaning that its closure, so the definition of a subset being dense is that its closure is the whole space. Pause and think why this is the case. Yeah, well, if you take an open subset U in X, not empty, and assume that it is not dense. So assume that U lies in the closure, and the closure is not the whole space X. Then you can write X as the union of the closure and the complement. They will intersect at the points that are in the closure but not in U. And so you have written X as the union of two closed proper subsets, and therefore it cannot be irreducible. Now, when working with the Zariski topology, or when we're working with algebraic sets in general, you have seen that we have the geometric side of the story, where we look at points of algebraic sets, and the algebraic side of the story, where we look at ideals and coordinate rings. So we want to be able to characterize algebraically, or at least have an algebraic look on connectedness and irreducibility. Let's start with connectedness and quickly move on to irreducibility. So what would it mean, what would it imply algebraically if you have a disconnected algebraic set? So if you have an algebraic set that is disconnected, so that can be written as the union, x1 union x2, where x1, x2 do not have any common points, and they are closed proper subsets of X, then the coordinate ring of X will be the product of the coordinate rings of these two. So why is that? Well, this will use a fact known as the Chinese remainder theorem that you have probably seen in some shape. If you haven't seen it in this shape, you can just assume it and believe it. We will not put so much energy into this. The Chinese remainder theorem says that if you have a ring, unital commutative ring, and two ideals whose sum is the whole ring and whose intersection is the zero ideal, then the whole ring is the isomorphic to the product of the quotient rings. So we want to show that these properties hold for the things we are interested in. So to do that, we take the ring R to be the coordinate ring of our algebraic set X, and we take Ji to be the the ideal rather, that defines these two, either of these two algebraic subsets. So Ji will simply be the vanishing ideal of these xi for I equals 1 and 2. So we need to show that their intersection is 0 and their sum is the whole ring. But the intersection of these two ideals, this is the ideal of their union, which is the ideal of X, and the functions on X that vanish on all of X, this is the 0 function. On the other hand, the sum of these ideals, has the following property. If we take the radical of this, we have seen that this is the ideal of the intersection. But since we assume they are disjoint, this is the ideal of the empty set. So this is the whole ring. And if the radical is the whole ring, then the ideal itself is the whole ring. And so the claim follows from the Chinese remainder theorem. Now, connected sets are important, but I would say more important for us in this course at least will be irreducible sets. So let's look at an algebraic characterization of irreducibility. Then we have the following proposition, that a non-empty algebraic set is irreducible if and only if its coordinate ring is an integral domain. So let us prove this. Assume that it is not an integral domain. So if O of X is not an integral domain, then since X is not empty, we know that this is not the 0 ring. So we just need to, so we know that there are 0 divisors. So then we have F1, F2 in O of X not 0, such that F1 times F2 is 0. And then if we set X1 as the vanishing set of F1 and X2 as the vanishing set of F2, then these two are closed and they are not equal to the whole space X because F1 and F2 are not 0. So these are closed proper subsets, and indeed X is the union of these because X is the vanishing set of 0, and 0 we could write as the product of these two functions, and this, as we have seen before, is the union of their vanishing sets. So this is X1 union X2. So then X is reducible. This proves one direction, and conversely, if X is reducible, so then X is the union of such X1, X2 with x1, x2 closed proper subsets of x, then we know that because they are proper subsets, we have this bijection between algebraic subsets and ideals. So it tells us that this is not the zero ideal for neither of them. So we can choose non-zero. So take f1 to be some non-zero element in the ideal of x1 and do the same for x2. But then f1 times f2 vanishes on x, because f1 vanishes on x1 and f2 vanishes on x2. And so in this algebra, f1, f2 is 0. It's a zero function. And since these were chosen to be not zero, and that was possible because the sets were proper, this shows that these are zero divisors. And so O of x is not an integral domain. And this proves the claim. And so recall that a quotient of a ring by an ideal is an integral domain if and only if the ideal is prime. And as an exercise, prove that if an ideal is prime, then it is radical. Shouldn't be difficult. So remember we had this bijection, according to the Nullstellensatz, between algebraic sets and radical ideals. We've already seen that points correspond to maximal ideals under this bijection. And now from this proposition, we know that irreducible sets correspond to prime ideals in this ring. And you can relativize this. So instead of looking at algebraic sets in AN, you fix some algebraic set to start with, and there, in the same fashion, it will follow that irreducible algebraic subsets of X that are not empty correspond to prime ideals in the coordinate ring of X. Now, one other notion that is useful for the Zariski topology is that of a noetherian topological space. So a topological space is called noetherian if every descending chain of closed subsets terminates, meaning that we cannot have a chain of one closed subset, say C1, containing properly C2, containing properly C3, and so on, cannot continue indefinitely. Such a chain will terminate at some minimal closed subset. And what is known about such spaces? Well, any subspace of a noetherian space, noetherian topological space, is noetherian. And the reason is simply, if you cannot have any infinite descending chain of closed subsets, then in particular you can't have it in a subspace. Algebraic sets with the Zariski topology are noetherian. This is because the coordinate rings are noetherian. So this is because if you have, so now we're looking at algebraic sets, so these are V of I1. If you have such an inclusion that goes on forever, this corresponds to an inclusion of ideals that goes on forever in the other direction, and this contradicts the fact that the algebra is noetherian. And so this also motivates the name noetherian topological space. What is good about such topological spaces is that they have a unique decomposition into irreducible subsets. So if you have an noetherian topological subspace, then there exist non-empty irreducible subsets, so that X is the union of these. And if you make sure that you remove any subsets contained in other subsets, then up to permutation, this decomposition is unique. So I will give a short oral sketch of the idea of the proof. So why does such a thing exist? You might want to pause and think before you listen. Well, assume not. What that would mean is, well, in particular, if X doesn't have a decomposition into irreducible subsets, it has to be reducible. So you can write X as X prime union X bis. And then if X doesn't have a decomposition into finitely many irreducible subspaces, then one of these will have the same property. So you can play the same game and write this as a union and continue indefinitely. And this contradicts noetherianity. And uniqueness is proved by assuming that you have two such decompositions, and conclude that each irreducible subset must be included in exactly one irreducible subset on the other side, and do this mutually to prove uniqueness. I leave the details to you.